Our Lesson 43 homework was to find the orientation or the configuration or the condition that will lead to measuring 0G simultaneously on the X, Y, and Z axes. Our Lesson 44 homework was to drop the IMU and have the Pico W code calculate the starting height based on the time spent at 0G. In Lesson 40, we learned that when the MPU 6050 is stationary and flat in the X and Y directions, the full force of gravity strikes the Z-axis sensor at 90 degrees. The full force of gravity pulls the Z-axis proof mass and the sensor substrate down toward the center of the Earth. Whatever support the IMU is sitting on will prevent the substrate from moving, but the proof mass, mounted on a spring suspension, will be pulled down, compressing the springs. The IMU circuitry translates that reduced distance into a Z-axis reading of 1G. Now, if we remove the supporting surface, for example by dropping the sensor, the force of gravity will be able to pull the substrate down along with the proof mass. The springs will return the proof mass and the substrate to their default position. The IMU circuitry will report that distance as a Z-axis reading of 0G. If the IMU is still flat in the X and Y directions during freefall, we'll have the answer to assignment 43. To solve the lesson 44 part of our assignment, we are required to drop the IMU and have the program determine the duration of the freefall portion of the drop. The program will then calculate and report the height from which the breadboard was dropped. I expect to ignore the X and Y axis data, but any rotation in X and Y axis will reduce the amount of the force of gravity striking the Z axis. This could affect our calculation of the duration of the drop, so before releasing the breadboard, we'll have to hold it as steady as possible in the X and Y directions. Also, we'll have to ensure a clean drop so the IMU does not experience any acceleration other than the acceleration due to gravity. With these constraints in place, we can use one of the standard kinematic equations for motion in one dimension with constant acceleration to calculate our starting height, h. h equals v initial times time minus 1/2 gt squared. The initial velocity, vi, is 0 because we start with the IMU at rest. So the equation reduces to h equals minus 1/2 gt squared. We know g, so once we know the duration of our freefall, we'll be able to calculate h. I decided to run the Pico W on battery and drop the breadboard from a height of about 3 feet. Unfortunately, that means the shell is unavailable. A push button was added to Paul's hookup to help manage the program. The push button is configured to create a hardware interrupt. In the interest of speed, we'll just collect data during the drop. The program collects X, Y, and Z accel values from the IMU along with a microsecond resolution timestamp and saves these values in arrays during the drop. When the drop is complete, the program cycles through the arrays, writing them to a data file and looking for the first abrupt change in consecutive Z-axis values, signifying the beginning of the drop. It then looks for the next abrupt change, indicating the end of the drop. Finally, the program reports success or failure and gives the user the opportunity to make another drop. The user can erase the existing data files or leave them in place and put the data from the next drop in a new data file. Let's have a look at the code. As usual, we start with imports. We import MPU 6050 because we're using the IMU. We import I2C because the MPU and the OLED are I2C devices. We import PIN because we're using the push button. SSD 1306 because we're using the OLED display. GC because we're doing garbage collection in the while loop. OS because we're going to be using Pico W file system. And time because we're using time.ticks and sleep. Here we define variables as shown. The push button is configured to cause an interrupt, so it needs an interrupt handler. That's manage button. The interrupt handler needs access to previous button release, delete old data files, and system mode variables, so they are declared to have a global scope. As soon as the interrupt handler starts, we reset it to none to prevent re-triggering the handler if the button happens to be pushed while the handler is executing. We compare the time since the last button press to 1 second as a basic denoising of the push button. A valid button press will change system mode to whatever the next mode is and set delete old data files to true when appropriate. We reset the previous button release variable and the interrupt handler before we return to the main program. The push button itself is declared on line 48. The hardware interrupt is declared on line 49. The interrupt is triggered when the push button state is falling, and when the interrupt triggers, the handler routine manage button that we defined earlier will run. Here we configure the OLED and the IMU as we've done in previous assignments. Before we hit the while true loop, we display the assignment title on the OLED and set the previous button release to the current time. This variable is used by the ISR to validate button pushes. After some garbage collection and clearing the OLED, what we do in the while true loop depends upon system mode. When we're in delete old data files mode, we display a message on the OLED offering the user the choice of pushing the button to erase existing data files or waiting to keep them intact. A progress bar marks the passage of time through the for loop. If the user pushes the button, the ISR will change delete old data files to true and system mode to create data file. And when we return here, we'll break out of the for loop. If the user doesn't press the button, the for loop will eventually run out and system mode will be changed to create data file anyway, but leaving delete old data files still set to false. Data files for this project end in .imu. When we're in create data file mode, we set file count to 0. Then for the list of all the files in the Pico root folder, we find any members that end in .imu. If delete old data files is true, we delete the .imu files as we find them. Otherwise, we just count them. Regardless, we finish by incrementing file count one last time and use that value in the file name of the current data file. We display a drop data will be written to message on the OLED and change system mode to ready to drop. Once we're in ready to drop mode, we reset our data variables and arrays, and we display a push the button then drop the Pico message. The program then waits for the user to press the button. At that point, the ISR changes system mode to capturing data. When we're in capturing data mode, we display a press the push button to stop capture message and add a timestamp and the XYZ acceleration values to the appropriate arrays. We increment number of drop samples by 1 in every cycle through the while true loop. When the user presses the push button, the ISR changes system mode to save analyze data. In save analyze data mode, we open the data file, write a one-line text heading, then cycle through each element of the arrays, updating the OLED, writing the data to the file, and evaluating each sample, looking for the start and stop of freefall. The noise in the data makes simple less than 1 comparisons ineffective. Setting lower limit for 1G less than 1 lets us deal with ZXL data which is less than 1 even though the IMU has not been dropped yet. Simply comparing each ZXL sample to lower limit for 1G to signify the start of freefall proved to be unreliable. From time to time I found that subsequent samples would increase in value rather than continuing to reduce. Perhaps I was shaking the breadboard after starting data capture or letting the board nosedive or roll as it fell. A better approach seemed to be to declare that the free fall has started if the current sample and the next sample are both less than lower limit for 1G. We declare that the previous sample is the end of free fall if the current sample is greater than 1.5G. We use the absolute value conversion to help cope with the sign changes that can occur when the breadboard bounces and or rolls over during landing. If we determine a last 0G sample, then we calculate the drop height. When we're finished analyzing all the data, we write first 0G sample, last 0G sample, and the drop height to the file, close the file, and change system mode to display results. When we're in display results mode, we display a success or failure message and the drop height if there is one. The user is offered the choice of pushing the push button again to run another test. Let's see how it works. We can start by pressing the push button to erase old data files and set the data file name variable back to accelerometer01.imu. Or we can let the loop time out if we want to keep the existing data files and increment data file name to the next available number. The progress bar tracks our position in the loop. Either way, we wind up in the ready to drop mode. We steady our grip and press the push button to start data capture and drop the Pico. Once the drop is complete, we press the push button to stop data capture and start saving and analyzing the data. If we never achieve 0G, we see a message about that, but since we did drop the Pico, we see the results of the data analysis and an option to do it all again. For each sample, a timestamp and an X, Y, and Z acceleration value are saved in a CSV file on the Pico. The CSV file can be read by Excel. Prior to the drop, we can see that the X, Y, and Z data are fairly stable. Starting at sample 21, you can see the ZXL start to drop. ZXL reaches 0G at about sample 23 and stays in that range until the IMU lands at sample 34 and all sorts of random bouncing takes place. Using timestamps 21 and 34, we can calculate the duration of the drop to be just over 0.44 seconds, and the equation h equals 1/2 gt squared tells us that the drop distance was 3.2 feet. The breadboard was released from a nominal height of 3 feet. Taking off a couple of inches for the landing pad makes the real drop distance more like 34 inches. We ran the experiment 4 times with the results shown below. All the results are longer than the real distance. If I had to speculate, I would say that the placement of the battery was rolling or pitching the IMU as it fell, artificially reducing ZXL, making the drop seem longer than it really was. And here's the answer to assignment 43. Drop the IMU. If the IMU is relatively flat, all 3 accelerations will be 0 during freefall. So, the Pico code to determine the height of a drop functioned with a 7 to 11% error, and we are able to find a circumstance where all 3 IMU axes would read 0G at the same time. Not a bad result. Any and all comments are welcome. Don't forget to like or dislike the video before you go, and feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.